Welcome everybody back, and let us continue with a further part of the chapter. Before now, we have discussed about the stability belt and how does the number of neutrons per Z, that is the atomic number, changes and its ratio, and the Z can be written as the number of protons. So N by P ratio is it. So there's nothing to be confused about that. So let us now get quickly into the next part. So there are three types of decays. Now, why are these decays? You might have heard about the C14 or the carbon dating method. That's a method that was discovered by a scientist named Wilfrey. I think so. The name was something like that. And the person, he got Nobel Prize for it, of course. So now let us understand why there are these types of decays. So let us take an example of an element that I can explain is uranium. Okay, let us do something. I'll explain it visually. So there is this atom, I mean a nucleus. Now we'll talk about the nucleus, and there is this nucleus that has its N by P ratio somewhere around 1.8. It doesn't go that much away, but still we can say 1.75 or something like 1.65 somewhere. So now what it will do is it will try to reduce this ratio to such an extent by a process of decay such that its N by P ratio becomes nearly 1.6, because directly making it 1 would be impossible because it's a nucleus and there are other electrons in the shell that we have to consider too. So we try to bring our ratio around 1.6, and an if an element has n by p ratio as 1.6, it may gradually go into decomposition and release something in such a way that its ratio becomes 1.5, and a 1.5 can't go jump to 1.0, that is 1, because that is a very drastic change. So now that you understood this, I'll write this as a transformed sign. So I'll complete this diagram like this, fill in some random element and make some bigger one. Change in ratio. And now what we'll do is sometimes we will change the number of protons and sometimes we will change the number of neutrons. So there would be a change in the ratio because some people, students have a misunderstanding that change in the number of neutrons or protons would make the ratio the same, but that is not it. So let us understand types of decays that I was talking about, that releasing of another element. Types of decays. There are in all three types of decays that are major. One is an alpha decay, one is a beta decay, and third is a gamma decay. Now, the beta decay is of two types, that is of beta plus decay and beta minus decay. And gamma decay occurs always in unstable atom. And now let us get deeper into what all of this means. So now the first one is the alpha decay. We'll take an element x that has its, this is a and this is z, and after some time it decomposes into another element y such that it releases an alpha particle, and an alpha particle is an helium nucleus, that is He2 plus, or I can write it as He42. This is the representation. And now by conservation of mass, here is A and here is 4, so as to balance both sides I have to write here E minus 4, and here downside I have to write Z minus 2. This is because of conservation of mass, and along with that there is heat that is evolved. So let us take an example. There is a uranium 235 uranium metal, and it has here 92, and on standing it would give 4 He2, that is an alpha particle, 231 thorium 90, and some energy. And now let us see the N by P ratio over here is 235 minus 92, yes, upon 92, and over here it is 231 minus 90 upon 90 is N by P ratio, and that is over here 3, 9, 10, 11, 12, 13, 4, 143 upon 92, and over here it is 1, 9, 10, 11, 12, 13, 4, 1 upon 90. So over here the N by P ratio, I'll use a calculator to calculate it. And now if you see, I have calculated it, and there's this minute difference, and this is what I'm talking about, that in nuclear physics things are very minute. Anyways, now let us understand something else. That is, for this was the example that I'm ending. So 4He2 would indicate that the mass of alpha particle is 4 times mass of proton, that is, and also the charge of alpha particle is 2 times E, and E is a number that we defined as the mass, I mean the charge of a proton, and that is the modulus, that a mod of charge of a proton, that is equal to the mod of charge of an electron. And now let us understand what this Q is in this equation. So this, let us just imagine, just close your eyes, and I'm not writing anything now. So there is this atom that is very large, just like uranium, and now it disintegrates into 2 other atoms, that is a helium and a thorium atom. So what does this relate you to? Does this remind you of a bomb explosion numerical, that at first the bomb is kept at rest, and then it is in 2 parts, and so this means that this heat is in the form of kinetic energy, and this helium and thorium would move in exactly opposite sides. But how would we prove it? So I'll write it. And I'll conserve energy. I'll first conserve the momentum. Initially, momentum was 0, and finally it becomes mass of alpha into v of alpha plus mass of y. I'm writing in terms of this equation into velocity of y. So this indicates that mass of alpha, v of alpha equals to minus of mass of y, v of y. So this means one thing, p of alpha, that is the momentum of alpha, is equal to momentum of y, and let us write it as a p. So p of alpha equals to minus p of y equals to p. Q that we write is the kinetic energy of alpha plus kinetic energy of y, and we can write kinetic energy in the form of the potential, the momentum as, I'll write it now how we can write. So I'll derive it over here. So half mv square, I multiply by m and divide by m, so it is half 2m. mv square is p square, so we got it here, p square by 2m. So p square by 2m, p square of alpha upon 2 times mass of alpha plus p of y the square upon 2 times mass of y is the q. So q is equal to p square plus y square. We know that p square of alpha equal to p square of y from this equation. So we write it as, I'll take something common like p of alpha the square, and then 1 upon 2 times mass of alpha. I'll take the 2 also common, p square by 2, 1 upon mass of alpha plus 1 upon mass of y, and then from now on we can solve the question. Like, the data would be provided to you, and accordingly you can solve the question. This is for advanced concepts and concepts that touch higher level. And so now we can find the kinetic energy of alpha from here in terms of q or in terms of y, something like that. So now again the scientists got curious. They were mind-blowingly amazed by what just happened over here. But now what they saw was this mass AXZ 4HE2 plus E minus 4Y Z minus 2. Yes. In this, when they calculated the mass, they expected an equation to be like this, and they got the equation like this. They were getting the energy and all, but there was a little bit of difference. There was a mass defect. That is, in some cases they found extra mass, and in some cases they found less of mass. So where did this mass go away? And here comes in Einstein's brilliant theory of relating our energy with mass, that is E equals mc square, which is a very wrong form of writing the equation. Einstein defined mass as energy by square of velocity of light in vacuum. This is what Einstein defined, and we'll be learning it that way. So Let us know what our mass defect is. So it would be mass of x minus mass of alpha plus mass of y. It can be positive, it can be negative at times, as I said. So we know E equals to mc square. From here we can, like, afterwards we can shuffle. And E equals to delta mc square. If we put delta m into the equation, we get it like this. And this is going on in joule, what you are calculating, to get it in mega electron volt. There's a ready formula that scientists calculated, that is delta m c square into 931.5. Yes, this is a ready formula that has been given. And very important one, and now let us see what a beta plus decay is. No, beta plus is a bit new because there is a new term in there, so I'll keep it for surprise. Beta decay. Let us start with beta minus decay first, because there is a new type of particle there in beta plus, so we'll explore it afterwards. Here also there is one, but over there are two, like a positron and a neutrino. So let us first go. So there's this element exz, and if I see it in point of a beta minus decay, so where does this beta minus decay occur? When the n is greater than, n by p ratio is greater than 1, there's this beta minus decay. And how does this happen? So there's an ejection of an electron. Okay, we understood it. So what would be the y? By conservation it will be a0, so a, z minus 1, so here z plus 1. We are just conserving the masses, nothing else. This is easy, important equation to know. Yes, I'll put in star. And one more thing that happens, let us wait. So now again, this is what the scientists expected, and what they found was there was something else that was missing. There was something, you might have heard about the spin quantum number somewhere in atomic physics and atomic in the parts of atoms. So Wolfgang Pauli, he suggested that there was a particle that had no mass, but it had only spin momentum, and there wasn't any type of energy conservation going right in this place, and hence we introduced a new particle according to Wolfgang Pauli, and we put in an antineutrino. I'm writing it as, and I'm writing it down, antineutrino. We here write self. And now the equation is complete. So now let us just understand what just happened over here at this point. There's this z, then this is a minus 1, z plus 1. How did this take place? So n by p ratio is greater than 1. So as for it to decrease, for decreasing, we can reduce number of neutrons and further making n by p less than 1. Sorry. So how does this happen? So there's this one neutron, and it gets converted into a proton and an electron. So now if you see 0 plus 1 minus 1 cancelled, 1 1 0 conserved. This is the brilliance of science. We predicted something and we got some different results, and now we are trying to explain what that is. This is what actually science is trying to do all the time. Now let's move further to the second part, that is a beta plus decay. And now in this there is an atom, and in this decay the n by p ratio is less than 1. So as for it to make it 1, we try to increase a number of neutrons. And how we do it? There's this axz, to which we write a y z minus 1. We reduce the number of protons, and now to balance there's this z minus 1. So there should be a plus 1 here, and here there's a0, and this is called as a positron, something you might be hearing for the first time. This is just like an electron, but not an electron. It has a positive charge. And then further there is a neutrino. Oh, that sign is for anti. So there's this neutrino, and this is something that's important again. And now let us understand what happened once again in this bottom part. So there was this one proton in X which got transformed into one neutron and one positron. And also there was a neutrino there. So what is a neutrino and an antineutrino? As I said, you have heard about the electron, proton and neutron, but this is something new. So antineutrino and neutrino does not have mass, charge, and even it is invisible. And the third thing is it is invisible. And the fourth thing that is important is it carries only spin momentum. Again, Wolfgang Pauli came in and he said, oh, wait a minute. This does not have energy conserved in this reaction. So where did that energy go in the thin air? No, it didn't vanquish anywhere. There are some particles, and this is proved in the laboratory, that there is something known as the neutrino and antineutrino. You can see in other experimental videos that they have proved about the presence of antineutrino and neutrino. But that's it. We don't have to look into it that much. And the third is the gamma decay. So in gamma decay, what happens is there's this axz, that is like axz, and there is gamma radiation release. There is energy evolved in the form of radiation, and if any type of decay occurs, then gamma decay occurs compulsorily. So what does this gamma decay mean? If alpha or beta decay occurs, that means that nucleus is in excited state. And now, from as we saw in the hydrogen spectrum, that an electron is excited. An electron is excited from its lower orbit to higher orbit, and then after going up, it also comes down again to its original orbital state. That is going from the excited state again to ground state, then radiation release in reaching ground state. Is gamma radiation. Now let us understand about the next concept, that is radioactivity. This is the end of the types of decay. Radioactivity is our next concept. So first point to note is radioactivity is a random process. And a radioactive nucleus can decay anywhere from its time of birth till infinity. And we cannot predict the time of radioactivity, like it would show decay at this time or like that. So there is this law of radioactivity that Rutherford and Soddy, another scientist, you search about him in Google, he also did remarkable contributions in the field of science and technology at that time. So there is this law of radioactivity, and according to it, the rate of disintegration of nuclei is directly proportional to number of nuclei present at that time. And this law is made by experiment, like discovered by experimentation. They tried for various elements, various atoms, and then they discovered it. So we can write minus of dN by dt is directly proportional to n. Why there's a minus? Because there is a loss of nuclei. That would be like n final minus n initial. The final ones would be less. Hence, it would delta n would be negative. So we add a minus sign by default in differentiation according to that rule. There's a minus there. And now minus dN by dt is equals to lambda times n. And what is then lambda? This is a proportionality constant called as decay constant. It is a material dependent quantity. So now integrating this, as it is a random process, I am integrating minus dN by dt from 0 to infinity. No, sorry, from particular period n0 till n, and over here from 0 to time t, that is lambda into dt, and I am taking this over here, so there's an n, taking the operators on their own sides. Now operators are separate, so I can write log of n minus log of n nod equals to minus lambda t. And if I rearrange this from log formation, n upon n nod equals to minus lambda t, and another form is n equals to n nod e minus lambda t. This is a very famous form, and most of the questions are asked based on this. Radioactivity is very important. So now that we understood radioactivity, let us go further and understand about half-life. This is the representation. So n equals to n nod e minus lambda t. So now putting t as t half, we get here n nod by 2 half. For that we are putting n nod by 2 equals to n nod e minus lambda t. So n nod cancels out, and then 1 by 2 equals to e to the power minus lambda t. Then taking log on both the sides, there's log of 2 equals to minus lambda t into log is 1. So minus minus cancel, log 2 equals to lambda t, and t equals to log 2 by lambda. This is another very important formula in this chapter. I've seen various questions on this type. Then how are we defining then lambda? We are defining lambda, it is reciprocal of time. As if you see, this should be unitless. So as t is second, lambda should be 1 upon second, that is second inverse. So that all things apart, we can say that. So now let us just derive it at first, and then we'll write the definition. N equals to n nod e minus lambda t. I am writing lambda equals to 1 by t, therefore all this gets cancelled, and then it becomes e, therefore it is n equals to n nod e to the power minus 1 by t into t. So tt gets cancelled, and we get n equals to n nod e to the power minus 1. So n equals to n nod by e, which is n equals to 0.36 times n nod. So n is 36% of n nod. So we can define it as like this. Reciprocal of time, lambda is reciprocal of time when 36% of nuclei is remaining. I've seen students making mistake over this part, so I highlighted it like that. And another formula is number of nuclei after n half-lives, and the formula is nth is n nod upon 2 to the power n and now if we start to plot the graph, then the graph goes something like this. Here is our n, and here is our T, and the graph goes something like this. Let me draw it with a bright color. Yes, this is a perfect graph, stunning one, and it starts at some constant. It isn't infinity actually. I'll edit it. Oh, now it's a bit okay. So it starts. Now this point, it is t half first wala, where it is n naught by 2. Then over here it is t second, where t equals to 1 upon lambda at that point. Here it is 36% of n naught, and all the graph goes on shrinking. So actually the element never decomposes. It takes infinite amount of time to decompose a particular radioactive element. Let us understand what activity is. So activity, I'm denoting by R, is minus of dN by dt. So R being the activity, now I'm in, I'm like, this is proportional, and now I'm writing minus dN by dt. We derived from the previous formula over here, dN by dt. Above over here first starting. Dn by dt is proportional is equal to lambda times n. So putting that lambda times n over here is lambda times n, and radioactivity is lambda n or e to the power minus lambda t. Then if this, then this, both are the same. So when t equal to 0, r equals to lambda n naught. Let this be r naught, initial activity. So r is equals to r naught e to the power minus lambda t. This formula is just like the formula previous, and yes, that's it. We'll discuss more in depth about activity in the next episode, and the further things like the binding energy, then mass energy equivalence, nuclear fission, working of a nuclear reactor, nuclear fusion, understanding how the reactions are carried out in the sun, and much more interesting topics too. Till then, meet you. Adios and a good night.